Welcome all to today's lecture. Myself Assistant Professor Tukur Gupta from Ajay Kumar Garg Engineering College, Ghaziabad. The lecture series that I am covering is for the subject Embedded System. Subject code is KOE 062 and this is open elective. Today I will be teaching non-preemptive scheduling schemes, which is a part of RTOS, that is real time operating system. In the previous lecture, we discussed that what are the differences between the multi-processing and multitasking systems. So, non-preemptive scheduling is a part of multitasking systems. There are various schemes which are available for multitasking, like there are cooperative multitasking, preemptive multitasking and non-preemptive multitasking. So, today we will discuss about non-preemptive scheduling schemes in multitasking systems. So, what is task scheduling? In multitasking system, there should be some mechanism in place to share the CPU among the different tasks. So, the way the CPU should be shared among the different tasks, this is known as the scheduling, how to schedule the CPU and to decide which process or task is to be executed at a given point of time, which is known as task or process scheduling. So, task scheduling forms the basis of multitasking. So, without scheduling the multitasking cannot take place, because there should always be a scheduling mechanism that how the CPU is being switched between the various tasks and on what basis and how the CPU is allocated to different tasks. So, this scheduling mechanism is very important. So, the scheduling policies forms the guidelines for determining which task is to be executed and when. The scheduling policies are implemented in an algorithm and it is run by the kernel as a service. The kernel service or application which implements the scheduling algorithm, this is known as scheduler. So, now we will talk about this particular scheduling scheme. So, the scheduling basically depends on that. Depending upon the scheduling policy, the process scheduling decision may take place, and when this decision is taken place, that when there is a switching between the different states. So, these are the switching scenarios, like maybe a task is switching from the running state to the ready state, blocked state from the running state, ready state from the blocked state, or finally the completed state. So, these are the various switching scenarios between the various states. The task scheduling policy can be preemptive and non-preemptive or cooperative. When we will discuss about the non-preemptive scheduling, we will see these 4 types of scheduling. So, this is number 1, first come first served, that is FCFS, or we can call it as first in first out, that is FIFO scheduling. So, last come first second scheduling is last come first serve, that is LCFS, or last in first out scheduling. Third type of scheduling is priority based scheduling. So, there are certain unique priorities which are assigned to different tasks, and based on the priority those tasks are implemented. Last type of non-preemptive scheduling is shortest job first scheduling. In this case, the tasks are scheduled based on the execution time taken by that particular task. So, these 4 types of non-preemptive scheduling we are going to discuss now in subsequent lecture slides. Firstly, we will discuss the very common and very first scheduling scheme, that is first come first served, FCFS, or we can call it first in first out, that is FIFO scheduling. In this type of scheduling, it allocates the CPU time to the processes based on the order in which they enters the ready queue. So, there is a ready queue and the tasks which are entering the ready queue first, they will be executed first. So, based on their entry into the ready queue, based on that only the CPU tasks will be executed. The first entered process is serviced first. So, that is why it is known as first in first out or first come first served. means the task which is which enters the ready queue first will be serviced first. It is same as any real time real world application where queue systems are used. So, in the queue, like in the ticketing system, so whenever there is a queue system, so this is the queue. So, the person that is entering the queue, so this is the queue, this is the front of the queue. So, here the person which is standing in front of the queue will be serviced first, then next, then next, then next, and so on. So, the person that is entering the queue first will be serviced first. So, this is known as the first come first serve scheduling. What are the drawbacks in this scheduling? It favors the monopoly of the process which does not contain any input output operation. It will keep on being executed until it finishes its task. So, in this way the monopoly is there, that a particular task which is not in the need of input output device will keep on using the CPU, and it will block all other tasks, that is the all other tasks will not be able to get executed. So, in this monopoly prevails. In general, first come first serve favors CPU bound processes, and input output bound processes may have to wait until the completion of the CPU bound process. So, if the currently executing process is a CPU bound process, then it will keep on executing. This leads to poor device utilization. So, in these are certain drawbacks, that a particular task will keep on executing until it gets finished, or if the particular task is a CPU bound process, not the input output bound process. So, it will keep on using the CPU for the unlimited time. The average waiting time is not minimal in this type of scheduling algorithm. We will understand this scheduling algorithm with an example. So, 3 processes with process IDs P1, P2 and P3 with estimated completion time 10, 5 and 7 milliseconds enters the ready queue together in the order first P1, then P2 and P3 will enter. Calculate the waiting time and turnaround time for each process and the average waiting time and turnaround time, assuming that there is no input output waiting for the processes. So, now we will understand the scenario that first of all P1 will enter the queue, then P2 and then P3. The execution time for P1 is 10 milliseconds, for P2 it is 5 milliseconds and for P3 it is 7 milliseconds. Now, we have to calculate the average waiting time and average turnaround time for all the processes. Now, it is here it has tried to figure it out, like assuming the CPU is readily available at the time of arrival. Now, first of all the waiting time of P1. So, P1 as soon as the P1 enters the queue, it will get executed because there is no input output waiting time. So, for the waiting time of P1 will be 0 milliseconds because there is no other task being executed before P1. So, as soon as the P1 arrives in the ready queue, it will get executed. Now, second task is P2. The waiting time for P2 is 10 milliseconds. How? Because the execution time for P1 was 10 milliseconds. So, as long as the P1 will get executed, P2 has to wait. So, the waiting time for P2 becomes 10 milliseconds. Now, next task comes is P3 here. So, P3 has to wait till P1 and P2 both gets executed. So, the total waiting time for P3 is equal to 10 plus 5, that is 15 milliseconds. Now, the average waiting time can be found out by adding all the waiting times for all the processes and dividing by number of processes. So, the waiting time for all is 0 plus 10 plus 15 divided by 3, that is 8.33 milliseconds. Now, we will calculate the turnaround time. How it is done? For P1, the turnaround time is 10 milliseconds, that is waiting time was 0 and the execution time was 10 milliseconds. So, in total there is 10 milliseconds. Now, turnaround time for the second process is 15 milliseconds, that is the waiting time was 10 milliseconds and execution time for P2 was 5 milliseconds. So, in total it takes 15 milliseconds. Now, turnaround time for P3 is the waiting time for P3 plus execution time. So, the waiting time for P3 is the execution time for P1 plus P2, that is 15, and 7 milliseconds is the execution time of P3. So, the waiting time 15 plus is execution time, that is 7, it will give 22 milliseconds. So, in this way we are able to find the turnaround time for all the processes. Now, we will calculate the total average turnaround time, that is turnaround time for all the processes divided by number of processes, we will get 15.66 milliseconds. So, in this case the average waiting time was 8.33 milliseconds and average turnaround time is 15.66 milliseconds. Now, we will come to the next scheduling scheme, that is last come first served, that is LCFS, and last in first out, LIFO. So, you can call it by any of the names. So, in this scheme, this is just the opposite of the previous one. So, the person that has entered the queue in the last will be executed first. So, this is just opposite of the normal queue system. The last entered process is serviced first. LCFS scheduling is also known as last in first out, where the process which is put last into the ready queue is serviced first. The various drawbacks can be seen here. It favors the monopoly of the process, because the process which does not contain any input output operation continues its execution until it finishes the task. So, again as similar to the case in the first come first serve, the task will keep on executing until it gets finished, and it and as long as it is a CPU bound process. In general, LCFS favors CPU bound processes, and input output bound processes may have to wait until the completion of CPU bound process. So, this leads to the poor device utilization. Average waiting time is not minimal. So, this is similar to FCFS, just the sequence is different. So, here also the minimal waiting the time average waiting time is not minimal. Again we will understand the scenario using an example. 3 processes with process IDs P1, P2 and P3 with estimated completion time 10, 5 and 7 milliseconds respectively enters the ready queue. So, assume that only P1 is present in the ready queue when the scheduler picks up it, and P2 and P3 entered the ready queue after that. Now, a new process, there is a twist in this scenario, that now a new process P4 with estimated completion time 6 milliseconds enters the ready queue when after 5 milliseconds of scheduling P1. So, when the P1 is scheduled, after the 5 milliseconds have passed, another process, that is P4, enters the queue with the estimated execution time equal to 6 milliseconds. So, this is the scenario. Now, same we have to calculate the average waiting period and average turnaround time. Let us see how is it calculated. Initially there is only P1 available in the ready queue. So, P1 is available and the scheduling sequence will be P1, P3, P2 and P4, yes, P1, P3 and P2. Now, what happens? P4 enters the queue during the execution of P1 and becomes the last process entered the ready queue. So, now since we are studying the last in first out, so we have to see that the process which enters the ready queue in the last is executed first. So, the P4 becomes the last process after P2 and P3. So, it is executed first. So, here it comes before P3 and then P2. Let us discuss now. Again the waiting time for P1 is 0 milliseconds because it starts executing as soon as it enters the queue. Now, waiting time for P4 is 5 milliseconds because after the scheduling it comes after the scheduling of P1 it comes after 5 milliseconds. Since the execution time of P1 is 10 milliseconds, so the time left for the P4 to start executing is 5 milliseconds. So, suppose here P1 is scheduled, its average its execution time is 10 milliseconds. In between, that is after 5 milliseconds, P4 is scheduled. So, as long as this P1 is being executed, it has to wait, P4 has to wait. So, for how long the P4 has to wait? For 5 milliseconds. So, in this way the waiting time for P4 is 5 milliseconds. Waiting time for P3 is, let us see, waiting time for P3 is 16 milliseconds, because 10 milliseconds are taken by P1 and 6 milliseconds are taken by P4. So, in this way the waiting time for P3 is 16 milliseconds. Now, again waiting time for P2 is 23 milliseconds, because P1, P4 and P3 have to execute, then only the P2 will get executing. Average waiting time becomes the addition of all the waiting times of all the processes divided by 4, because there are 4 processes. In this way we get 11 milliseconds average waiting time. Now, we will calculate the turnaround time. So, turnaround time is the time spent in the ready queue and the execution time. This is the total turnaround time. So, for P1 the turnaround time is 10 milliseconds, because it needs 10 milliseconds for its execution. For the turnaround time for P4, it takes 11 milliseconds, because the time it spends in the ready queue is 5 milliseconds and the execution time is 6 milliseconds. So, in total it is 11 milliseconds. Turnaround time for P3 is 23 milliseconds, the time is spent in ready queue and time is spent for its execution. Turnaround time for P2 is time spent in the ready queue and the execution time. So, we will see how. For P2 the waiting period is 10, for this 6 and then 7 and execution time is 5. So, in total it takes 28 milliseconds. So, the average turnaround time for all the processes is P1 plus P4 plus P3 and P2 divided by 4. So, in this way the total turnaround time is 18 milliseconds. So, here total average waiting time is 11 milliseconds and average turnaround time is 18 milliseconds. Now, we will talk about priority based scheduling. In this, a priority which is a unique or same associated, it is associated with each task. The priority of a task is expressed in different ways, like a priority number, the time required to complete the execution, etc. In number based priority assignment, the priority is a number ranging from 0 to the maximum priority supported by the operating system. The maximum level of priority is operating system dependent. So, priority is assigned to the task on creating it, and it can also be changed dynamically if the operating system supports this feature. So, based on the requirement, the priorities of the tasks can be dynamically changed according to the need, and so the different tasks can be executed according to the requirement. The non-preemptive priority based scheduler sorts the ready queue based on the priority and picks the process with the highest level of priority for execution. So, in this way the different tasks are prioritized, and this information is is given to the ready queue, and accordingly the priorities, according to the priorities the tasks are arranged in the ready queue and they are executed accordingly. The drawbacks are similar to the shortest job first scheduling algorithm. Non-preemptive priority based algorithm also possesses the drawback of starvation. What is this starvation? This is a scenario where a process whose priority is low may not get a chance to execute if more and more processes with higher priorities enters the ready queue before the process with the lower priority starts its execution. What is this scenario? Suppose a higher priority task is being executed, and in between that is the high priority task is being executed and the low priority task is waiting for the CPU. Now, as soon as the higher priority task was going to get over, but before the low priority task could have started, another higher priority task keeps on entering the ready queue. So, in this way the low priority task will not be able to get any chance to get executed, because the more and more processes having the higher priorities will keep on entering the queue. So, this is the scenario of starvation. The starvation can be effectively tackled in priority based non-preemptive scheduling by dynamically raising the priority of the low priority task or process. So, this can be done based upon the features of operating system, whether the operating system is able to do this or not, that the priorities can be dynamically changed according to the condition, and so the low priority tasks can be prioritized to complete their execution. So, the technique of gradually raising the priority of processes which are waiting in the queue, that is ready queue at the time, as the time progresses, for preventing starvation is known as aging. So, this process of dynamically raising the priority of the tasks is known as the aging. Let us understand this scenario using this example. There are 3 processes with the process IDs P1, P2, P3 with estimated completion time 10, 5 and 7 milliseconds, and priorities are 0, 3, 2. That is, the one with the lower number is having the higher priority. So, here 0 is having the highest priority and 2 is having the that is 3 is having the lowest priority. So, they enters the ready queue together, calculate the waiting time and the turnaround time. Let us see how we are able to calculate it. So, in this way the task with the highest priority, that is the 0. So, P1 is having the highest priority and P2 is having the lowest priority. So, in this way P1 is arranged first, then P3 and then P2. So, the execution time of P1 is 10 milliseconds, P3 is 7 milliseconds and P2 is 5 milliseconds. So, the waiting time of P1 is 0 milliseconds, P3 is 10 milliseconds and P2 becomes the addition of the both the times of executions of both the processes, that is 10 plus 7. So, 17 is the waiting period for waiting time for P2. So, in this way the average waiting time can be calculated as 9 milliseconds. Now, we talk about the turnaround time, that is the total waiting time and the total execution time. So, the turnaround time for the process 1 is 10 milliseconds, for P3 is 10 is the waiting time and 7 is the execution time, that is 17 milliseconds, and the turnaround time for P2 is the waiting times for both the processes and the execution time for itself, that is 17 plus 5, that is 22 milliseconds. So, in this way now the average can be calculated by adding all the all the turnaround times and dividing the number by 3. So, 16.33 milliseconds is the average turnaround time. Now, we come to the next scheduling mechanism, that is shortest job first. It allocates the CPU time to the processes based on the execution completion time for the tasks. The average waiting time for a given set of processes is minimal in SJF scheduling, optimal compared to other non-cooperative scheduling like FCFS. So, this is somewhat more efficient scheduling mechanism, because in this the task which is having the less execution time will be executed first. So, in this way the tasks having the less execution time will be executed very fast, and then they can give the time to other tasks waiting for their turn. So, in this way this is more efficient as compared to the previous ones. The drawback is the process whose estimated execution completion time is high, that may wait. So, again this condition may be there. So, even if the more and more processes with the least estimated execution time enters the ready queue, suppose the processes which are entering the ready queue are having the lesser execution time as compared to the task having the large execution time, then the task with the larger execution time will keep on waiting for the CPU. So, this condition may come. So, may lead to the starvation again, with the now difficult to know in advance the next shortest process is ready queue for scheduling, since new processes with the different estimated execution time keep on entering the queue at any point of time. So, this may be the scenario that the processes or the tasks with the lesser execution time keeps on entering the queue, and so the condition of starvation can be there. Now, we will understand the scenario using an example like P1, P2 and P3 are the 3 tasks with this much completion time, and they enters the ready queue, and now in between a new process P4 with the estimated completion time of 2 milliseconds enters the ready queue after 2 milliseconds. Assume all the processes contain only CPU operation and no input output operations are involved. Let us find out how this will be solved. So, at the beginning there are only 3 processes, that is P1, P2 and P3 available in the ready queue. Now, and the short SRT scheduler picks up the process with the shortest remaining time for execution. So, this is the specialty of this scheduling algorithm. So, in this example P2 with remaining time 5 milliseconds for scheduling. Now, the process P4 with the estimated executions completion time, that is 2 milliseconds, enters the ready queue after 2 milliseconds of start of execution of P2. So, the processes are rescheduled for this scenario. Now, P2 is being executed, after 2 milliseconds P4 will enter, and after that P2 again will be executed because it is left with the least execution time. So, then P3 will be executed and P1. So, the whole scenario has been changed because due to the entry of the P4 process in between, which is having the very small execution time. Since the process which is having the least execution time has entered the queue, that is why the priority has been given to that particular process. So, P4 will be executed just before the completion of P4 and P3 and P1. So, after P2, after 2 milliseconds of P2 execution, P4 will enter the queue, it will be executed, and then the rest of the P2 will be executed, because the leftover execution time for P2 is less than the execution time for P3 and P1. So, P2 will be completed first, then the CPU will be allotted to P3 and then the P1. So, this is the scenario. Again the average waiting time can be find out from the figure shown here, and same is the case for the turnaround time. So, in this way we can see that this shortest job first scheduling algorithm is the somewhat more efficient than the previous ones, and we were able to analyze the different scenarios of the average waiting time and the turnaround time for different scheduling algorithms in non-preemptive scheduling schemes. In subsequent lectures we will discuss about the preemptive scheduling mechanisms. That is all for today. Thank you.